great pleasure for me to be here. I would like to thank the scientific committee and the organizers for having me here. It's amazing to see all these participants in one place after a number of years. So yeah, everything feels great. So today I will give a talk, we don't let the title throw you off. This is basically an overview, since I'm given the time, of a project I've been following through the past few years, all the way since my PhD days in Cambridge with Michael Pilot and Ignacio Lopez Franco. So different parts of these things I've done with different collaborators. And yeah, today we'll give an overview of what's been going on, mainly in the most recent years. This is an outline of my talk. So we will start with the motivation story, the background story, what could be called the Sweedler theory for monoidal categories. So we'll start with monoidal categories. I will give some details, only the ones that are necessary for what's going to happen later. And then the main focus of the talk will be generalizing this Sweedler theory for monoidal categories with a double categorical context as a many-object generalization. Then, time permitting, we'll see how that goes. I will go into a weakening of the monoidal double categorical structure, but for a specific application in mind. So hopefully it won't be too high level and everyone will be happy. And we will finish off with some further directions. So the second part is joint work with Vanessa, who finished his PhD a couple of years back here with Marino. And the third one is joint work with Gavino and Gardner. Okay, this is not the topic of the talk, but this is the underlying theme behind the talk, well, at least in my mind. Okay, what is a B-enriched category? It has objects as an ordinary category, but then it has the home objects and the composition rule and the identities all belong to a different monoidal category V, and that's enriching its structure. Linear categories, two categories, linear categories, higher categories all begin from enrichment in V. Another structure one to look at is that of growth-ended vibration. So in that case, we again have two categories, but they are both ordinary categories, and it's just a functor between them. So in a sense, we can view the one as the top, the one as the bottom, as a base category, and every object and morphism above lies through this functor about something in the bottom. And what's special about this functor, the vibration, is that there exist some liftings that are called Cartesian. So for every morphism in the bottom category and say every object above the target, then there is this lift of the morphism up in the top category that has this unique factorization property. These are different, some people view them as different sorts of generalizing category theory, with a third one being internal categories. And in general, these do not go well together. I mean, they're not combined in an evident way, at least. But a common pattern in the results that we will see today is this picture, where on the left we have a vibration, on the right we have a non-vibration, and then the bottom and the top are enriched in one another. So this picture, trying to explain this picture that arose a couple of times roughly, we came across this idea by Bunka and Schulman, independently introduced in 2013, of the theory of enriched index categories. But that was a bit different because they had a fixed base, a fixed monoidal base, whereas here we have these two different bases, A and B, and also those bases were required to be Cartesian monoidal. The structure was the Cartesian product, and that was not what happened in our examples. So we have to introduce the theory of enriched vibrations that allow non-Cartesian bases, that allow different bases. So yeah, there is a definition. I'm not going to give this definition because that's not the subject of my talk, but I would like to remember that there is this underlying thing going around of a theory that combines enrichment and vibrations in a meaningful way. And today we're going to focus more on the enrichment side of things, but I should say that the fiber and the fiber structure is indispensable for proving the enrichments. So they're not separate in my mind. Okay, let's begin with the background story, the motivation story, where we have a fixed monoidal category V. Then we start looking at monoids, which are objects with multiplication and unit mass that are associative and unital in a strict sense. Those diagram commute. Plenty of examples everywhere in algebra. Rings, R-algebra, topological monoids, monads on categories, all these can be viewed as monoids. And then we have the dual concept. There will be a lot of dual concepts in this talk of the comonoids. So we have co-multiplication, co-unit, which are co-associative and co-unital. Again, there is a theory of co-algebras in algebra for many years, but also as a special or trivial case, in a sense, in every Cartesian monoidal category, every object can be viewed as a comonoid using duplication, the discard map. So in that case, comonoids are isomorphic to the objects of the category. And in fact, that's a characterization of Cartesian monoidal categories. Okay, with specific maps that preserve the structure and would be the reasonable thing to write down, these form categories, monoids and comonoids. Now we're going to start building some more structure on those categories to end up to the enrichment I have in mind. So first of all, if our monoidal category is equipped with a grading, then those two categories become monoidal themselves. And the grading is important because you can see there, points. Maybe I cannot point. It's not important. The first part of the map has the grading there so as to switch the monoid and the comonoid and for me to be able to apply multiplication there. Building with some more structure that we're going to need, so we will assume that this is also monoidal closed. So the tensor product factor will have an adjoint. So that, in the case of the setting where I'm now, induces, as a Lax monoidal factor, induces a map like this, a factor like this. It takes a comonoid and a monoid and gives the internal home the structure of a monoid, of an algebra. And again, we can think of it in terms of vector spaces, or we can think it in this general context, and this structure is called convolution. If I want to understand the structure by taking the adjunct of the multiplication, so taking the tensor product we see going down to A, we see that all the pieces of the structure are used there. First we apply co-multiplication of C, then the grading to switch the intermediate entries, then we evaluate twice, and then we multiply the monoids. So that's the convolution structure for the internal home between an algebra and a coalgebra. In vector spaces, of course, as a particular case, we get this well-known fact that for any coalgebra, taking the linear dual, so the homes out of it down to K, has naturally the structure of an algebra. So this is a special case of what I wrote above. But if one tries to do the same with a coalgebra, it's not true. So if I take the linear dual of an algebra, it is not naturally a coalgebra unless it is finite dimensional. And this has to do with the fact that the tensor of the stars is isomorphic with the stars of the tensor when we have the finite dimensionality case. So one way of fixing this asymmetry, if we want to view it that way, is the so-called Sweedler dual factor, or finite dual sometimes called. So we can define a circle, which is a subspace of the linear dual, and it contains maps whose kernel have a co-finite ideal. So the quotient space is finite dimensional. So this is a K coalgebra, and not only does this have the structure of a K coalgebra, but in fact we have this adjunction here. Sometimes these adjunctions that have the opposite of a category involved are called dual adjunctions because the unit and the co-unit are both looking in the same direction if we don't take the opposites. Okay, so this is all very standard, very well known. A way to view the next slide, which is the topic of measuring coalgebras, universal measuring coalgebras, is generalizing this adjunction there. So instead of having just maps going out from C to K, I can generalize K to an arbitrary algebra and take the concept of a universal measuring coalgebra. So those were introduced by Sweedler in his book, Hopf Algebras, back in 1969. The way they were introduced, those red TAB on the right-hand side, were not from an adjoint factor theorem or generalizing the slide before, but they were defined algebraically, and in fact there was a whole category of measuring coalgebras where it was proven that PAB was the terminal object. I'm not giving many algebraic details of this, it's all in the book. But now the idea is to generalize away from vector spaces, of course. Okay, we want to go to this more broad general categorical setting. And one way of doing this, I'm not saying it's the only one, but that was convenient for our purposes, was to go into local presentable categories. So having the grading I said before, monoidal closed structure, and on top of it have local presentability. In fact, these assumptions are the ones used throughout my whole talk. Surprisingly or not. So local presentability, local presentable categories are also very nicely behaving categories that are co-complete, and every object is a filtered co-limit of a certain set of presentable objects. So that allows us to move away from vector spaces to graded vector spaces, differentially graded vector spaces, so all these sorts of vector spaces, but also further away to our modules for a community grid and more settings that satisfy those conditions there. So the main result here that gives us the way to move forward is this, the fact that under those assumptions, the convolution factor I talked about earlier has this parameterized adjoint, which we call Sweedler, some people call Sweedler-Hom or universal measurement algebra factor. So parameterized means that this is a family of adjunctions for a fixed monoid. You see, the category of monoids is shared in the domain of those two factors. Okay, so the existence of this, establishing this adjunction, really uses the fact that V is locally presentable, and for example, by sulfide force, we can see that comonoids are locally presentable, and a locally presentable category is a great place to find an adjoint. If the target is if the domain is locally presentable, then that's really helpful for adjoint factor filters. Okay, so if one follows their nose, then this is, and writes down what an adjoint factor theorem would give in that case, then this is the common formulation of a measuring coalgebra. But for example, in certain cases of interest, in set, which is Cartesian monoidal, as I said before, and every object is naturally a comonoid, and we don't get anything new. We just get the set of monoid maps there. So there is nothing special going on here. In vector spaces, of course, it's the setting of Sweedler, and in fact, we can view all K-algebra maps inside the universal measuring coalgebra space, and they are precisely the group-like elements. So that's a nice characterization. And this point of view of saying that the universal measuring coalgebra is a generalization of K-algebra maps was heavily used 20 or 30 years ago by Bachelor to see some examples and some applications of universal measuring coalgebras in differential topology as an algebraic object. And finally, where I took the name Sweedler theory, I don't know if people like it, but there is a manuscript by Amel and Joyal back in 2013, which is called Sweedler theory for coalgebras in the Barkov-Bar construction, when they show that these two functors, these adjoint functors, along with the third parameterized adjoint and some tensor products and internal homes, they are, as a set of factors, related to various algebraic constructions in the Barkov-Bar adjunction for coalgebras, and they wanted to understand better causal duality, essentially. So, yeah, I borrowed the name Sweedler theory from that manuscript because it was a bit more compact than universal measuring algebras and enrichment or something like that. All right.
Just to make sure I'm following, if we take V, so in the setting of K vector spaces, if we take V to be K,
yes.
PAB recover the Sweedler dual?
Exactly. This is all a rationalization of the Sweedler dual factor.
Is there any way to understand how this formula has anything to do with the description you gave on the other?
Algebraically, you mean?
Yeah.
Well, if we go down to vector spaces, this formula has an algebraic description of a sum of coalgebras over the co-free coalgebra or the home of something. So I presume if you take K in that formula, that will give you the thing before. It was surprising for me that in the book of Sweedler, he gives both these things, both the Sweedler dual and the measuring coalgebra thing, that he never draws the connection. Yeah, so he says that the Sweedler dual is an example of an algebra, that measure, but nothing more to support this analogy. Yeah, but this is in fact a direct generalization of what happened in the previous slide, precisely. Okay, so to see how all this is related to the enrichment I started talking about at the beginning, we are one step away of using this adjunction, the convolution factor, with this established universal measuring factor, to see how this induces an enrichment of monoidal comonoids, of algebras and coalgebras. And this is established by noticing that the convolution factor is in fact an action of the monoidal category common on the ordinary category mon. An action here means that this factor is pseudo-associative and pseudo-unital, so the same thing as a strict action, but in the pseudo case. And I'm not going to get into details, but this is a standard fact that whenever we have an action from a monoidal category on a category, and this has an adjoint, then we naturally get an enrichment of the category in the monoidal category we started with. And in fact, this is even stronger. There is an equivalence between actions with adjoints and V categories equipped with the weighted limits of tensors. All this is in a very nice paper by Janelitz and Kelly in 2002, but in fact the main result goes way back in 1997 to a paper by Goldman and Power, Variation through Enrichment. In fact, I was enriching in a bi-category in the very general setting. Anyway, for us, what's important is that this convolution, in fact, having an adjoint, the measuring coalgebra adjoint, directly gives us an enrichment. And that's the end, in fact, because algebras become enriched in coalgebras using the convolution factor that has an adjoint. Okay? I added the symmetry thing there because originally we get an enrichment of the opposite of the category of monoids, and if we want a well-defined opposite V category, we need this to be a symmetry. Anyway, this is a bit technical. So yeah, this is the base enrichment that we're interested in, algebra that enriched in coalgebras. And before I finish off the story, the background story, with inserting modules and comodules in this picture, let me make a quick digression, just because I thought it was nice to put this result also in a completely different setting, completely different, at least when you first look at it. So it was Batista, Canapil, and Vercroise, here in Belgium, two of them, that introduced Hopf categories in 2016 as generalizations of Hopf monoids. Okay? And semi-Hopf categories are the many object generalization of bimonoids. We do not use the term bi-categories for clear reasons, so semi-Hopf was the next best thing. So what is a bimonoid, for those people that haven't heard? It is a monoid, a comonoid, both, so they have all these four structure maps that they get together in a specific way. One of the axioms to have an idea is that the multiplication is a co-algebra map, is a comonoid map in that way, for example. So now in the many object setting, one would like to pack this up with many objects, then one way of going, one convenient way of going, is to have a multiplication which is global, in which sense the indices do not stay the same, x, y, y, z, z, x, but then the co-multiplication, so the generalization, the pathing up of the co-multiplication is local, so A, B stays fixed there. And in fact, the axioms that are supposed to be satisfied are precisely of this form, only we have to be clear about what's happening with the indices in this diagram chasing definition. So in fact, the definition of a semi-Hopf category is precisely a category enriched in comonoids. And surprisingly or not, doing this completely other different thing of establishing algebras being enriched in co-algebras, we come down with a very natural example of a semi-Hopf category. So we can position algebras as a very meaningful, non-trivial example of a generalization of a bimonoid. Okay? So that was the end of the digression. Now we'll talk about Hopf things. Okay, let's finish off the story, the Sweedler theory story, by inserting some modules and comodules in the picture. Okay? So a module for a fixed monoid is only an object in my monoidal category equipped with an action. Okay, a strict action, associative and unital. Dually a comonoid comes with a co-action, and I have things on the left here. So this is a left module and left comodule, same side. Now, of course, they become also categories with specific kinds of maps, which would be exactly what we would expect in that setting. Oops. See those? Oh my god. Here. Just a simple module map for a fixed, for me, M and N being A modules, both of them. Now, we would like to introduce these categories that do not have modules for a fixed monoid, so not just have A modules there, but having modules for arbitrary monoids. Okay? So we can do that object-wise, no problem. Just take the objects to be modules of arbitrary monoids. But now the question is what to do about the maps. How are you going to map, how are you going to define a map between an A module and a B module? And now the answer is satisfying, I think. We need to include in our definition a monoid map. So we need a passage, in the last line there, we need a passage from A to B that essentially what this is doing is making N, my B module, it's making into an A module by restricting the scalars, as we said. So this is restriction of scalars using the monoid map F there. But this idea of restricting, of taking an A module and making it naturally into an A module in order to define the maps is precisely what lies behind the idea of agglutinative fibration. Okay? So both those categories, more than one, are agglutinative fibration and agglutinative fibration appropriately above the categories of monoids and comonoids. And with the reindexing factors, the factors that allows us to introduce those liftings I was talking about earlier are restriction and co-restriction of scalars in that picture. Great. The analogous results here, and that finishes off the story, is that under the same set of assumptions, then we have this convolution factor started off from the monoidal closed structure of the category that not only goes up to monoids, but it goes even further down to modules and comodules. So for every module and comodule, the internal home has a natural structure of a module, and again this has an adjoint, okay? And this is the universal measuring comodule. Algebraically, again, this has found applications in connection bubbles and loop algebras, but we're interested in the more high-level approach to this. And because of the same ideas of action-inducing enrichment things, we get an enrichment of modules and comodules. So, done. Here, we talked about an enrichment between the bottom side, so algebras and heuristical algebras, monoids and comonoids, and a bit hastily, but hopefully the ideas were vividly the same as what happened before. We have an enrichment of the global category of modules over the global category of comodules, but heavily using, although I'm sweeping all the details under the rug, the fibrational and the off-fibrational structure there to establish these enrichments. Okay? So now, we want to generalize. This is a very broad word with many different definitions depending on what you want to do. But for us here, we want to use this simple yet fundamental idea that a one-object V category has essentially the same data as a monoid in V. Okay? So ideally, we would like to, it works, to change this category mon to V cat. So to go away from the one-object case to the many-object case using the passing from monoids to V categories. I will show you the full picture there. I will define the key players in a second, but let me just show you the schematics of it. So this is where Picard is. Okay, you can see it, it's right there. And then everything else is supposed to be analogously the many object generalization of what's happening on the left. Now, for someone to go and do that, there are basically two ways, as it might be the case in many problems in category theory. One can go and work bottom up. So say, okay, I'm going from monoids to V categories. What did I need before? I needed local presentability of the base of the enrichment. Let's try and show that we have the same thing here. So this can be done. It's a little bit technical, but it's actually more straightforward. You see exactly where you're going, and you can generalize. But, and we all know it has its advantages, we would say, we're not just going to take this thing on the right, we're not going to establish the enrichments of these categories I have on the right, but instead I'm going to find a more general framework where this appears as a special case. And for me, this framework is the double categorical framework, which is going to appear in a little bit. So this is what's going to happen now. All these categories on the right will be examples of something more general, and then the advantages of this, of course, is that we can take the theory and apply it to a different context and get the same results without having to work out the details of every structure every time from the beginning. Excellent. Okay, so let me give you a little bit more details of what's happening on the right. The categories we all know, or we've seen, or we've heard of. So let me just say what I wanted to say here very quickly. So the composition rule looks like this, okay? This is all happening inside V. Now, if my V, my monoidal category V, has co-products, what will equivalency these maps, because they are there for every x, y, and z, by inserting a sum here. So I can say that this is equivalent, of course, due to the universal property, to asking for the existence of maps for every x and z. So the y's are only here. So this is the point of view that's going to lead me where I want to go, because then I can define V modules, which is a very standard concept, by the way. I can define a V module for a V category as an indexed family of objects in V, equipped with an action from a category AXY. If I want, in the presence of co-products, I can put the sum there as I did over there, okay, for some B category. So this is basically a one-sided bi-module, enriched bi-module, very standard, very old, very useful. So we don't have a right-hand side category acting on my module, and that's why I only have one set of indices there. I have NY. Okay, so now I want to dualize this to introduce this category of Vico categories. Sorry, this is the one-sided bi-module. So I want to, it's not the button I want to press, anyway. So one way of dualizing this, looking at this picture, is switching every arrow and saying that the Vico category in the presence of co-products preserved by the tensor consists of, again, is a set of objects in V equipped with a co-composition, dual thing to composition for V categories. And dually, what is a Vico module for a Vico category is the same with a V module, everything switched around using the sum. A very natural question at this stage would be, why are you so fixed on having the sums? Why don't you do something easier, which is the concept of a V of category? So a V of category would tell me to not take sums here and just say that a V of category is switching this on the other side and then having maps into the product, essentially, of this thing. I don't want to do this because, as many of us know, when V has some nice properties, V of does not have those nice properties. So if V is locally presentable, which is very essential for what we've been doing here, V of is not going to be locally presentable. So this is not a setting I want to go to because formally it's not convenient. Now the setting I want to go to is a context where categories, co-categories, modules and co-modules all live together as objects in a specific place. And that place is a double category. Okay? And I will say why a double category is more preferable for us than a bi-category, which would be another option here. Okay, I will not give you the full definition, unfortunately, but I will set my terminology. A double category consists of a category of objects, so it has 0 cells and vertical 1 cells. Looking at this picture, these are the 0 cells, everything around, and these are the vertical cells. So this part forms a category, an honest category, one category. Then it has a category, consists of a category of arrows. What is this? The objects of this category are arrows. So the objects are those arrows here with this line to separate them from vertical arrows, like this. And the morphisms in this category are those squares here. So they have boundaries. They go from A to B, but they also have vertical boundaries F and G. Both of these structures are categories, one category. Okay, so we can compose strictly and everything. I know that the original or the older terminology convention had those things vertically. Unfortunately, I followed the more modern approach and have the horizontal arrows going that way. Okay, and then we have some structure maps that give identities for these categories and how they work with each other. They give us source and target maps. So every map, every object and every map in D1 has a source and target in the vertical category. And of course, the very, very, very important horizontal composition there. And a bunch of actions that allows us to make all these things work together. This is the definition of a category, internal in the category of categories. Okay, so it is a fact, and a very useful fact, to connect double categorical stuff to bi-categorical stuff, that every double category in the world has a horizontal bi-category attached to it, so it's part of the structure. We're going to see it that way. How? The 0 cells are the same, the 1 cells are the horizontal ones, so in fact we're discarding the vertical structure, and the 2 maps, the 2 cells in the bi-category have this shape, but this and this are identities. And these are called globular cells. So this is an identity, this is an identity, this becomes a bi-category. And if I want to compose in a bi-category serially, then I would have not a strict associativity, but a pseudo-associativity of composition there. Okay, so that's important for getting all the new, say, ideas of double categories back to the very known and well worked out setting of bi-categories. And let's see the key players here. Before, we are fixating on monoids in monoidal categories, comonoids, and their modules and comodules. Let's see what will take the place of those things in the setting of a double category. Well, the Swift you've definitely seen before. What's going to be a monoid in a monoidal category here becomes a monad. So what is a monad in a double category? it is one horizontal arrow with the same source and target here, okay, as the set of objects, if we want to view it that way, and it comes together with multiplication and unit that are associative and unital. We can write down the actions as always. Notice that those things are globular, so they have identities going down. Of course, we can have the dual concept of a comonad, and these form categories of monads and comonads. Those things have been defined in the past by Schumann and by Keurig, Gabriel, and Koch, monads in double categories. But what's interesting here is the following. As objects, those things are the same as monads in a bicategory. Why? Because of the globularity of those things here, on the object level, we don't see what's new in double categories. It could be equivalently be established as something in the horizontal bicategory. Now, what's new is the fact that for maps of monads, this is a completely different concept than the one in the bicategories. And let me show you what I mean. So a monad map, having a monad here, and another monad here, they don't have to have the same set of objects here, the clearer thing, but they have to have the same vertical arrow here. So this is a monad map in D. Now, if I want to move to the horizontal bicategory of D, or in a bicategory, I don't have the vertical maps. This is part of the double structure that does not appear at all, in the first side at the bicategories level. So what would we do for a monad map? A very well established concept. We would have horizontal arrows here that allows us to change this. And in fact, this direction is called traditionally lax monad map. So, this direction is called a lax monad map. So for us, this is a co-lax monad map. Now the idea is that in certain cases, each one of these maps will give one of those maps, but not all of them are of this form. So the morphisms are very, very different. And why do we prefer to work with double monads than bicategories is precisely this picture. Because the categories I'm interested in are not captured by maps like this, but are captured by maps like this. So it is really important to allow on the level of arrows, because the objects are the same, to allow the level of arrows to have this flexibility with the vertical length going down. Okay? So let me write the result of what I'm talking about by waving hands. Yeah? Okay, the morphisms are different. Let's now look at a specific double category. What is the double category? This is the double category with object sets. Vertical arrows are functions. So the vertical category is very nice and very easy. It's the category of sets and functions. Now horizontally, those maps here are V matrices. V matrices are just indexed, families of objects in V. In fact, we can view them as functors from x times y down to V. But because x and y are sets, there is no extra structure in these families of objects. They're just families of objects. And then the horizontal composition is where this double category or bicategory takes the name. It looks like matrix multiplication. So if I want to compose two of those things, I have this sort of matrix multiplication composition going on there. So, in that double category of interest, specifically the monads are the categories and the co-monads are the co-categories. So the definitions I showed you earlier absolutely fit in this framework of monads and co-monads in double categories with an emphasis on the arrows. V functors cannot be captured wholly as monad maps in the bicategorical context, and that's why we prefer this setting. Okay? So double categories, advantages over bicategories, at least for us, for our example at hand. Excellent. Let's go a bit further and see what happens with modules. So again, we have to generalize from a module in a monoidal category to a module for a monad in a double category, and we do the evident thing. So on the level of objects, again, this coincides with the definition of a module in a bicategory. Because of globularity, because the vertical arrows here are just identities. So a module for a monad is an object, a horizontal arrow equipped with an action satisfying the usual axioms and so forth, so on and so forth. And now the maps again are different. The maps, now we have to think in analogy to what we said earlier about the global category of modules and comodules. We want to have maps not just between modules over the same monad, but we want to have maps between modules over different monads. So now I will have to have a monad map as part of the structure. to be able to shift from the one side, from the A module to the B module. And, okay, the categories that are formed with the morphism I wanted to talk about are like this. So if you want to have a closer look, if I can do that. This is an A module, this is a B module. The vertical arrow on the left is arbitrary, so it goes between the domain of those two things, which is a general set. We don't have any other information about this. But the map on the right-hand side is part of a monad map. This end is part of a monad map. Where is this monad map? Right here. So we need this monad map I wrote here. We need this monad map to be able to go from an A module to a B module. Okay? So these are the definitions of a map in this setting. Okay, bear with me, we're almost done. And we can start seeing the structure of the double category that allows us to do Sweedler theory. And in this setting, there are some subcategories of interest. So one could fix the monad, the same thing as the monoidal categories. Say, I'm not interested in this global thing, fix me the monad. If we fix the monad, this becomes the same as that. These become identities. So it looks like what I have there with the right-hand side being an identity. One could fix the domain, okay? So if we want to fix the domain, the thing on the left would be an identity, and the rest of the action would be the same. Finally, we can fix both the monad and the identity, and then we would have vertical arrows here, and vertical arrows everywhere, identities everywhere. So this comes down to the theory of modules in bicategories. We know that modules in bicategories are either more algebras for the monad, which is the precomposition with the monad A, and in fact, all these categories are monadic over specific other categories whose properties we know. So this is very convenient for us for transferring categorical properties of completeness, co-completeness up to the categories of interest there. To close up how this is the setting where everything we want to generalize comes together, it is the case that the category of B modules I talked about on my first slide, the previous slide that generalizes these modules, is captured by the category of modules in B map if I fix the first object to be just the star, the singleton. And then if one wants to see the general modules and comodules, we have those structures that are a little bit more involved. And I'm not sure I understand them very well, but they are what they are. So they look like a one-sided bimodule again, but on the right-hand side I have this Z. I have this Z that is not attached to a B category on the right. So it is like a bimodule, where the right-hand side is like a discrete B category on the set Z. I've not seen those objects before. If anyone has seen them before, that would be helpful. Okay. Sweedler theory for monoidal double categories is the title of the talk, and this is the result that it's actually referring to. So what is the result it's actually referring to? Is a direct generalization of what happened in the monoidal categories. That monads are enriched in comonads, and modules are enriched in comodules in double categories. And now the question is, before we had a fixated monoidal category V, and we said this needs to be what? Braided, monoidal closed, and locally presentable. Now we work in a double category D. What is the necessary structure to make this true? To make all these structures actually behave the way we're expecting them to behave and get the result of the generalization of Sweedler theory in the double categories. So there are four conditions that we need. Two of them are very well known to the people that have seen or worked with double categories before, and two of them are new. I'm going to go through them. The first part is the vibrancy. So this is a very nice property of double categories that allows us to turn vertical cells to horizontal one cells. Okay, fiber double categories, pro-arrow equipments, framed by categories, these are all come down to the same thing essentially in the end. So we have a compartment and a conjoint, which are horizontal arrows attached to every one of those vertical arrows we form. So in V matrices, that's very clear that that's the case, because every function gives rise to a V matrix with a very easy definition here that separates y and x depending on whether they are mapped through this function f. Okay, so what does this give me? Why do I need my double category D to be fibrant to get the result I want in the beginning of the slide? Because under these assumptions, I can see that modules are fibered over monads and comodules are all fibered over comonads. And the reindexing factors, in fact, are precisely generalizing the co-restriction and restriction of scalars I was talking about earlier. I said I'm not going to give details about the vibrational aspect of things, but I said that these are very important for establishing the enrichment. So we definitely need this to go on and see how these things are enriching one another. Okay, the other condition is the fact that D needs to be a monoidal double category. What is a monoidal double category? Well, a double category consists of two ordinary categories, so I'm asking of these two ordinary categories to be monoidal. And they have to have this interchange law between the monoidal structure and the horizontal composition, and another one that compares the identities. So being in the setting of a monoidal double categories, of course, gives us a lot of advantages. In VMAT, that's the case, because for sets, of course, the monoidal product, well, at least the one I'm using here, is the Cartesian one, and for V matrices, I have a point-wise sort of tensor product here. So it's true for VMAT, no problem. And then the result we get here is that comonads and comodules, remember, those are going to be the basis of the enrichment I have in the box above. So comonads and comodules need to be monoidal if I want to ever enrich them, of course. So they are monoidal, and let me just show you very briefly the monoidal structure, say, for comodules. And the only reason I want to do that is because this looks very much with what I had on my first slide. So I use the coaction to go here, but now the grading I had before becomes the interchange law. This is very indicative of what happens when I pass from a monoidal category to a monoidal double category. So here I can see how the grading, in fact, becomes a very important part of the structure, which is the interchange law of the monoidal structure of the double category. Symmetry is inherited if I need it, so that's nice. And now the two conditions that were not known to us, at least. We did some digging, and if anyone has ideas, I would be glad to discuss them after the talk. So the first one is the concept of I wanted to say a closed monoidal double category. I'm not going to say that, I'll tell you why, and I'm going to call it a locally closed monoidal category. So here I need a double factor. I'm calling it lax because of a specific direction of a comparison map. We're not going to get into details. But what's really important for us is that this double factor, in fact, makes both categories of objects and arrows, so the two component categories of a double category, they make it into monoidal closed categories. And the source and target being maps of adjunctions just let us have some control over how these two adjunctions on the top and the bottom behave with one another. There is a definition of a monoidal closed double category in a paper by Graves and Paré, adjoint for double categories. But it didn't work for us, and that's why we didn't use the same definition, because it didn't involve the internal closed structure of D1. And for us, that was very, very important. So we had some discussion with Bob Paré, he was very helpful. So we couldn't find a direct generalization of the one to the other, so we had to introduce this to actually make sense of what's going on. It is the case that in VMAT, we have this locally closed monoidal structure. So clearly set is monoidal closed, is Cartesian monoidal closed. And now for V matrices, I just give you this formula without much explanation, but it does what I wanted to do. It's using the monoidal closed structure of V, okay, and it also uses products in V. So here I have some F and G mapping, things like that. So it's not a weird looking formula, it's a natural thing maybe for someone that has worked with these things before. Why do I need the locally closed monoidal double structure? Because this is what's generalizing convolution for me. Before we saw that convolution factor was absolutely important for the adjoints being the universal measuring whatever, and for the enrichments to be induced because this was an action. So here, having this condition of a locally monoidal closed category, we can show that H induces factors between monads and comonads, and between modules and comodules, which are also actions. This is a direct generalization of convolution. The final part of the structure, which is even more, not suspicious, but I'm not very happy with it yet, is one of a locally presentable double category. Now, many people have helped us, have actually helped us understand what this is supposed to be. John Burke and Steve Blackvar in the audience actually have helped us understand what we need. The definition we have now is a sufficient one. So we have some conditions that make things work for us in a way that we're expecting them to be. But due to the lack of a general theory of locally presentable even bi-categories or two categories, I mean, I know there are some references in that direction, but there is not a treatment of this thing. And this is definitely not our purpose with this paper here, of having a formal treatment of locally presentable double categories. We will stay with what's sufficient for us and hope that in the future someone will actually take this task and see what a locally presentable double category should be, like formally and coherently, and why. So let me just show you our conditions. We have that, again, this is very important for us, D0 and D1 separately are locally presentable as categories, so we need this, and then we need that the source and the target are accessible at the joints, again, not a weird looking condition. We need the map, the function that gives the unit to be accessible, but not having a joint actually, and the horizontal composition to be accessible in each variable separately. Okay? So this is our working definition right now. I would hope it would be improved in the future. It is the case for VMAT, so set is definitely a locally presentable category. Finite sets play the role of presentable objects. Now VMAT 1 was trickier, but Steve Black helped us with that a lot, and there is a technique that actually works for many categories of interest, that we can express VMAT 1, for example, as a pullback along an isofibration, and then use the limit theorem to obtain VMAT 1 being a locally presentable category. This is more formal and more coherent than trying to pin down the presentable object in VMAT 1 and show that it is closed, under filter colimits and all these things. It's a high-level argument that is very helpful. Okay, and that's the end. This is how we finish with this story. Having these conditions, then these induced factors H, the convolution factors, both have adjoints. This is the generalization of universal measuring coalgebra and comodule factors we had before. So we do obtain the enrichments of monads and comonads and of modules and comodules in the general setting of a double category. Okay? So now the question is, great, we have this, we obtain, so everything can be applied in VMAT. So VMAT was our case of interest so far, and this is what we actually proved, that in this setting of a very nice double category that has these 4 pieces of structure we need, we can actually apply the theorem and get the desired many-object generalization of monoids, comonoids, and modules and comodules. Now the question is, what would you do if you wanted to move to different contexts? And as I said in the beginning, this high-level approach has the advantage of not having to reprove everything, but actually verifying those 4 pieces of structure for a double category to get another example of this. And what are we interested in? We are interested in the double category of V-symmetric sequences. So let me briefly recall what is this double category with a very, very well-known bi-category, of course. This is a many-object generalization of species. The objects are sets and the vertical ones are a function. So on the vertical side, we still have set, as we had in the matrices, no problem. Now the horizontal arrows change. They change a lot. And not having the matrices, we have colored symmetric sequences. So they're not anymore factors from x times y to v, but they are factors from the free symmetric strict monoidal category of x. I hope I said that right, times y to v. So now S of x is a category, it's not a set anymore, and the objects are n tuples of n tuples of objects in X, of elements in X. Now the 2 maps I just wrote them down, they're just the natural transformation between those things if you view them as factors. And the horizontal composition is a very big formula. I have it in a slide later, but I don't think we'll see. It's a generalization of the substitution for species. Why would someone want to move to that context of V-symmetric sequences? Because monads in there are very interesting. They are operands. So in the one object set, in the one object case, the one for species, we know that monoids in the category of species with the monoidal structure of substitution are operands, non-colored operands if you want. And now in the many object setting of V-symmetric sequences, they are symmetric colored operands or multi-categories. So one would like to look at them, to look at operands and co-operands and modules for operands and co-modules for co-operands, and maybe get some enrichment relations there that are related to the Barkov-Barra junction in the sense of an Elman-Joyal back for algebras. So this is the purpose. Well, we're not there yet. But now, someone would start very happily saying, okay, at least we spent all this time working our way for a general double category. So now we can apply to this new double category and get the results right away. Well, it's not as easy for the following reason. Vising is vibrant. We can actually find liftings of functions into symmetries in a specific way, but it's not monoidal double anymore. So we haven't even checked the other two conditions, the new conditions, but it fails right there. So it's not monoidal double. What is it? It's very interesting, I think. It is an O-plus monoidal double category. This is completely new, by the way. We introduced this definition. And what is it? So let me just say this. I'm not going to spend much more time on this. Oops. An O-plus monoidal double structure, which is what happens in these symmetries, looks as follows. In the monoidal setting, I only showed you the interchange law. So this existed in a slide before with an isomorphism in the middle, and I said that there is another one comparing the units. Now, we don't have isomorphisms anymore, but we only have a comparison map going that direction. Okay? And it's called O-plus because this is part of an O-plus double functor. This is just the name of the direction of the comparison map. Okay? I'm not going to give the definition, but this is what it is. Now, one would ask again, why would someone really, okay, this symmetry is a very nice example, overhead is a buzzword, I see the point here, but an O-plus monoidal double structure sounds like too much, like going high level for all these things. How does this fit with things we already know? And now I would like to draw your attention to the following analogy. A one-object double category with a single vertical arrow has the same amount of data as a monoidal category. So here is the generalization going down and realizing that the double category always gives us a monoidal category in that way. Now, if I wanted a monoidal double category where this is an isomorphism, this is an isomorphism, those two things become equalities for abstract reasoning, I can choose them to be equalities if I want. Then, if I go down to monoidal category, so a single object, single vertical arrow monoidal double category is a braided monoidal category, okay? And now the question is, what is an O-plus monoidal double category doing? Where an O-plus monoidal double category doing is precisely in the middle. A one-object O-plus monoidal double category is a duoidal category. So in the same way, if you've seen them before, when you have a monoidal category, braiding monoidal category, and now you separate the braiding in a sense, you obtain a duoidal category, two different monoidal structures that relate to one another with a map looking like this. Okay, this is the interchange for duoidal category. So really, an O-plus monoidal double category is not as strange as it looks, but it really fits in the general theme of things in a nice way. Okay, I'm not going to talk about the normality condition, but in fact, one needs the normality condition if we want the passage to bicategories, because we always want the passage to bicategories to see what's going on there. All the details are in the paper, in the manuscript with Camino and Gardner. But at the end of the day, what this work is doing is, the purpose is very clear. We want to show that the V-symmetries, this double category of V-symmetries, is normal O-plus monoidal. Okay? Again, we're not doing it by hand. I have the normal O-plus monoidal structure at the last to final slide, but the concept is obtain this from a machinery that produces O-plus monoidal double structures. And what is the machinery? It is a Kleist-Lee double categorical construction. I'm not going to say more, I'm going to go straight to the future directions here. But the idea here is, start from a monoidal double category. We know them, we prefer them. They give us monoidal bicategories if we want, if we have some extra assumptions there. Start with a monoidal double category and take a monad, in this case is the free symmetric strict monoidal monad I talked about earlier a little bit, and find a monad which has a couple of pieces of structure there. Every time you apply this monad to the double category and you do a Kleist-Lee double construction, very much similar to the classic construction for ordinary categories or for bicategories, you will get an O-plus monoidal double category. Apply the Kleist construction to a pseudo-monoidal structure, you get an O-plus monoidal structure. So that's exactly what this work is about. I'm going to skip through these details here because I think I'm taking a lot of your patience and attention, in fact. And let me just go. I should say that about the Kleist-Lee construction, the double category, this appears in this form, almost this form, in a paper by Campbell and Schulman, in 2010, I think. But here we built a monoidal structure on it, so that was very nice, building on the previous works. And let me just go to some future directions here. Okay, I started with this and I'm ending with this basically. I said I have the Sweedler theory for monoidal categories that has this enrichment of monoids, modules, and everything. We pushed them all the way to the double categories, but it looks it's not enough, because if I want to apply it to symmetric sequences to go to operands, I really have to extend the theory or edit the theory a little bit to cover oplex monoidal double structures. Disappointing? No, I don't think so. I think it's nice, it's fruitful. You keep working on things and see what's really important. Maybe the pseudo-monoidal double structure was an overkill. Maybe we didn't need it at the beginning. So we need to work out if the theory works the same way for this weakened version of a monoidal double category. And then, of course, we have to check the rest of the conditions for B-symmetries, the locally monoidal closed and the locally presentable condition. It's going to take some work. And then let me just say that at least for the one object case, not for B-symmetric sequences, but for species that I get mentioned from time to time, we have worked out with Ignacio a couple of results that show us that this is in the right direction. So we have some enrichment of operands and co-operands, for example, under certain assumptions that show us that yes, you're going in a good direction. In the many object case, we are expecting to find very similarly flavored results like that. I think I'm going to close up here, and thank you very, very much for your attention.
Let's take just one question.
Thank you so much for your talk. You may have answered this in your talk, but I got so interested that I couldn't hear everything. So the thing about monoidal double categories, you told us that what degenerate ones are they degenerate something else's?
You mean the one object case?
Are monoidal double categories one object?
One object monoidal double categories are braided monoidal categories.
Are they one object version of something higher?
If I said that, I didn't mean it.
I'm asking.
I don't know if monoidal double categories are one object case of something else. I really don't know. That sounds very interesting. I really don't know.
You said they were braided?
A braided monoidal category is a monoidal category equipped with a switch. So A times B is isomorphic to B times A. Yeah, it's almost like a symmetry, but a little bit more relaxed.
Did you say that was what a degenerate double category was?
A degenerate monoidal double category. So monoidal double category, monoidal double category, and then the oplex in the middle. So monoidal category is braided and duoidal in the middle.
All right, let's thank Christina again.